Great. If that's it, then the next speaker we're going to have is Dr. Otto Lappi. He's going to talk about predictive processing in naturalistic task domains. Thanks, BrAIn.
Okay, thank you, Ben. Do I have a clock somewhere to time myself? There, okay, thank you. Right, so my name is Otto Lappi. I come from the Cognitive Science Unit at the University of Helsinki. So today I'm going to be talking about the human side, somewhere between the brain and the AI, human mind, and a particular way of looking at it. I'm going to be discussing two of our projects, one that has just recently ended and another one that has just begun. So we are interested in human behavior and the human mind in natural task domains. I'll spend a few minutes here explaining what I mean by natural task domains, and then I'll spend a few minutes explaining what I mean by predictive processing, and then I'll give you one example of a model that we have done in this line of work. So, first of all, what is cognitive science? Cognitive science is a scientific enterprise that tries to understand human mind and behavior and brain function by conducting experiments. We collect brain data or behavioral data or physiological data, and then we want to produce some kind of model of the underlying processes that produce that behavior or brain data or physiology. So we want to understand the human mind in a kind of quantitative way, and for this, artificial intelligence and the development of computer science in the past decades has given a lot of tools for cognitive scientists to try to wrap their mind or wrap science around human behavior and brain function in a more precise way. Now, my interest in particular is in human behavior in natural task domains and trying to understand or model human behavior in these kinds of tasks. So what do I mean by that? Dancing, swimming, pole vaulting, driving, mountain climbing, skiing, motorcycling, music, cooking. I mean things that people actually do. When you look at what people do outside of the laboratory, I want to understand some of those kinds of behaviors. And my particular interest is in car driving. We do experiments. Here you see a video excerpt or a video frame from one such experiment where the participant is driving in the wild on a real road. And this is a picture from a head-mounted eye tracker, so you have a head scan image and the participant's current gaze direction is indicated there in the red. Most of the time when people drive, they look at the road. That's the qualitative discovery, but we want to go a little bit deeper. We want to understand how the visual world is sampled in such a way that the brain has then the ability to decide, for example, where to steer the vehicle. Now, then when you look at people's behavior in these kinds of tasks, dancing, swimming, driving, what you see, or well, what we cognitive scientists at least like to think we see, is that when you compare human performance in these kinds of natural task domains to machine performance, humans are at a very, very high level. So even tasks which we feel are quite simple because we are very, very good at them. Our brain has a sophisticated capacity to drive a car, and therefore we feel it's quite a simple task. But actually, when you then look at robotics and autonomous cars, it's a huge challenge computationally to build machines which can do the same thing that humans do. There's this thing called Moravec's paradox, which basically says that things that humans tend to find easy, like cooking or driving a car, are very, very difficult, often for machines. And then things that are comparatively straightforward for machines, like chess, comparatively. Of course, it's been a huge effort to try to make machines play chess, but that is something that machines seem to be very good at, and that is very difficult again for humans. So that's one of the motivations for the interest in how does the human brain then cope with the complexity and ambiguity of these natural tasks that seem to be so difficult for machines. Here are some of the characteristics of natural task domains. So analyze a little bit of what I mean by natural task domains. So the stimuli are rich and complex, not just peeps or isolated words or flashes of light to respond to. There are often many action possibilities which are not necessarily obvious. Humans bring their own goals and task knowledge. This is very important, that you are trying to understand the knowledge that has been built into the human brain through millennia or millions of years of evolution. And also an important point, these tasks are generally dynamic, so you are interacting with this complex environment in a very sophisticated and subtle ways, which compares then to the traditional lab-based way of looking at human mind and human behavior, where you take the person out of the natural task domain, put them in a lab, give them some sparse stimuli and an instruction to behave towards these stimuli in a particular way. And often then you also present the stimuli not in an interactive manner, where the person interacts with the stimulus world. The stimuli just come to the participant one at a time. And that then is conducive to analysis in the kind of traditional experimental way. But what you are losing then is the view of humans in these complex natural task domains. You are losing sight of the question of what is it that makes humans so good in these computation-unfriendly task domains of the real world, because you are presenting the human mind with a computation-friendly, restricted aspect of the world. Okay, so that's in a nutshell what I meant by natural task domains, and then what I mean by predictive processing. So many of you probably have heard about this. I can demonstrate it with a kind of a simple example. So if I ask you to respond to my not wrapping this table, so I do this, and you are supposed to respond as fast as you can. I can present you these stimuli. It's very important that I give them in time somehow randomized, and then you try to respond as fast as you can, and we find that you have a physiologically limited response time that you cannot go under, somewhere on the order of half a second. Now, if I ask you to respond to the fourth wrap, so you're supposed to do yours on the fourth. Now, if I ask you to do that, then you can respond to the fourth wrap with 0 reaction time, or even negative reaction time. You can anticipate the fourth knock, and that's because there is some pattern now that you are being able to observe. And that means you can anticipate the final stimulus that I am then looking the response time, the reaction time in relation to. You can anticipate it. However, anticipation is not exactly the same thing as prediction. So what I have shown here is an anticipatory behavioral response. But that anticipatory response can come from either a process in your mind that predicts from this pattern where and when the fourth knock is going to come, and that would be predictive processing, controlling your response. Or you can respond to the first few knocks. I am giving you 3, and if you start responding with a rather large latency to the first 2 knocks, you can still give an anticipatory response, but without prediction. So by predictive processing, I mean precisely those aspects of anticipatory behavior, which is what most of us do most of the time, which are specifically based on prediction. And there's this predictive brain idea, which many of you probably have heard also about, is that what the brain is trying to do all the time is to predict its own next stimuli, the next stimuli it's going to see, or predict the feedback it is going to get from action. Because if the stimuli are not given as a preset sequence, but are produced by interaction with the dynamical world, then all the stimuli are going to be feedback to what you are doing. I move my head and my view around the world changes, and this is feedback that tells my brain that my head has actually moved in the way specified. And then you can get those responses. You have here the action. It's kind of cheating. The arrow action doesn't come from anywhere, but you can think of the action as being generated by multiple kinds of processes in any real-world scenario. So you could have action generated directly by feedback, which would be reactive, reflex-like control, or for example, proportional control in feedback control theory. Then you could have action driven by prediction error, where the higher levels are trying to predict what feedback is going to come. That is compared to the actual feedback. This generates a feedback prediction error, and that can be used to drive behavior in active inference. Or you can then have the predictive models themselves driving the action, which I would call then model predictive control, which is the framework which we used in the example I'm going to be talking about in the rest of here. Yeah. So this view, I just emphasize, is different from from looking at the person or the brain as a system responding in the traditional fashion. And here, in a nutshell, is the basic idea of predictive processing for those of you who are not familiar with it. So there's this hierarchy of these predictive models. The higher levels are trying to predict the feedback that's coming from the lower levels, and the lower levels report the prediction error to back to the higher levels. Okay, I'm going to skip the next couple of slides, which are there for discussion if we need them, and then I'm going to go to the example of the model we have. Okay, so this is a model that we produced, or postdoc Jami Pekkanen produced in a recent project which we had with the traffic engineering unit, and this is what the model looks like. Oh, there's a lot of lag here, so I'm getting a big feedback prediction error here. So this is quite complicated. I'll try to give you the lowdown in 1 minute what you're looking at here. So this was a car following task, and you have these agent-based car following models that are put into traffic engineering models of traffic flow, where you look at how congestion is created and so on. And what you have here at the bottom is a traditional, basically a traditional agent model of car following, where you have these, no, this isn't working. Oh, no? Okay. So a model that responds to events in the environment. You have some environment variables, distance to the leading vehicle, on speed, relative speed compared to the leading vehicle, and then the traditional model, which is the control bit here, would respond to these variables. And this gives you the world and a reflex interaction with that world. And then what this project was about was this top level, where we have then the cognitive bit to make it more human-like. So what the system has is, first of all, it does not directly obtain from the environment these variables to control the behavior. It obtains a noisy noisy and transformed version of those variables. For example, a human cannot determine the direct distance of the leading vehicle by some kind of sonar or something. We estimate it from the visual image, from the angle, and that projection causes a different structure of noise to the input to the brain. So the perception noise is not the same as the noise in the physical variables. And then you have here, a system then trying to predict the next feedback that is coming. That's the core of the predictive brain or the predictive processing idea. It's not necessarily trying to predict the future, it is trying to predict its own next input or its own next perception. And then learning is driven by the prediction error, the discrepancy of the predicted perception and the actual perception, in a way that takes into account then the noise of the perception, so that, for example, if the car is very far away, the angular substance is very small, this will be a very noisy measurement, and if the state model says that the car is far, then any discrepancy is weighted less than when the car is nearby, and the brain would know that it would get more accurate, less noisy information about the distance. Right, and then this is used to drive the behavior, and in such a way that, well, I'll not go into the most interesting bit because I'm probably going over time already. Yeah, so I'll just say that there's a cool solution in this model to the problem of which environmental variables and which state variables are the relevant ones. Because we have a motor control unit, we can determine for each different state that the world might be, according to the state estimate, which actions would be taken. And only the information that makes a difference to the spread of actions to take are the ones that need to be actively sampled by perception, by controlling the perception, so that you don't have to keep a veridical, complete model of the brain all the time. You just have to keep the parts of the model that make a difference to what you need to do next. Okay, thank you. And I suppose we don't have any time for questions if I'm over time.
We'll take a question if we have one.
Okay.
One question. Yeah, can we have the box? Throw it.
I'll hit sunglasses.
Thank you very much. I am Margit Sutra from the Collegium for Advanced Studies here in Helsinki. Just started yesterday and very interested in AI ethics, but also in relation to this, actually, I would like to ask you, are you also interested in more complicated reactions? For example, you are looking at driving of the cars, and for example, also about the reaction when it is related to our emotional response. For example, when we are talking about self-driving cars, that they could avoid, for example, street rage. They are not getting emotional. They are not doing these bad things that humans are doing. Is this also something that you are interested in? And is anybody in Helsinki working on this? Because this could be also my wider interest.
Okay, two-part answer. So that is something that's really difficult then to examine in an experimental setting. So the way this model was developed, we had participants come to an experiment, 40 participants, I can show you a picture, where they drove a real car and this occlusion was used to measure when they felt they need to see the car ahead and when not. Obviously, it would be more realistic to use eye movements, but then you have to model peripheral visual perception as well. Okay, 40 participants would drive in this scenario of following a lead vehicle, and then they would do the same task in a virtual reality 3D simulation, and then the model being developed would drive the same simulation game engine as what the human drove in the VR experiment so that you can compare those directly and then validate it against the field data. Now, if you want to study road rage, you can't really use this kind of approach because, well, you can't get participants in an experiment and ethically induce rage. And even if you got the ethical permission, you probably couldn't do it because I mean, how do you get people to behave in such a way in an experimental situation? So you really are more reliant on getting data from like actual traffic behavior, and because we are interested in this nuts and bolts modeling of the simpler behaviors, this is already quite complex. So that is something that can't really be answered with this paradigm, I feel. But if you are interested in the ethics of AI, then I would refer you to the Moralities of Intelligent Machines research group, also in cognitive science, led by Michael Laakasuo. So I can give you his details, or you can Google him up.
All right, thank you very much, Otto.